Cool. So now we are going to cover the Grignard reaction, and we haven't done this yet in SI. This is part of chapter 12, yes, and right now I'm using the chapter 12 handout. So I am going to spend a little bit of time on this, but hopefully not too much. So first we're going to talk about the difference between a nucleophile and a base. We already said earlier, anything with a negative charge is a nucleophile or a base. And so we know that nucleophiles and bases both like a negative charge. And I'm going to do like a little, not a Venn diagram, but one of these things. So nucleophiles are going to attack electrophiles. So they're going to make a new bond to a different molecule. Whereas bases steal hydrogens. So the similarity, they both like negative charges. They're both doing some kind of attacking. But the nucleophile attacks an electrophile, whereas the base is only going to steal a hydrogen. And, alright, so the questions are a little bit in a weird order here because I usually just draw it out and then we go back and answer the questions. So I'm going to add a page right here. Oh my gosh, if my iPad could chill for a minute. Okay. Anywho's, technical difficulties have been fixed. So we're going to start with an alkyl halide once again. And we're going to use a reagent we haven't really seen before. Magnesium and ether. Ether goes under the arrow. We don't really care too much about it. We don't do anything with the ether. All you need to know is the magnesium. All right. So I'm going to paint a little picture for you. We're going to have a mini soap opera about the Grignard reaction. And hopefully that'll stick it in your brain and it'll never be forgotten. So, we had our happy little couple here, carbon and bromine. They're bonded to one another. They're very happy. And then all of a sudden, magnesium comes in, and magnesium is a hoe. So magnesium is going to break them up. It's a home wrecker. And so it's going to come in, and it's going to slide right into the middle of this. So it slides right into the middle of their relationship. And so now we actually have this. Right? So on the outside, from the outside perspective, it looks like carbon and bromine are still together, but magnesium's just meddling in the middle, right? But what's actually happening is carbon lost the love of his life. He's really sad. He's negative. Sad face. But bromine is out living his best life with magnesium. So there's a positive over here. And so that's why it looks like they're together, because we have the strong minus and the strong plus, but there's actually not a real bond. So we can think of them as two separate units. All right. I need my own TV show. Thank you. Thank you. All right. So basically, in science terms, we have this alkyl halide. Magnesium comes in, it breaks this bond, and it makes almost like a pseudo bond. And it looks like so, but we're going to draw it like this, because this is actually how we want to think of it. And so this right here is considered the Grignard reagent. And someone asked if I'm recording. Yes, I am. So Mg doesn't have a negative charge in the beginning. Or it might. Where's magnesium on that? No, I think it starts off with a positive charge, actually. And, okay, so the positive charge is actually here. And that's why it has this, like, association. But for my, story that I built, it made more sense here. You guys don't have to know where the plus charge is here. It does not matter to you. This is all that matters. But yes, you're right. The plus charge would go here. And magnesium would have been positively charged in the beginning. Cool. All right. So now that we have the Grignard reagent, we can actually start doing the Grignard reaction. So that was just like the pre-Grignard, right? This was just season 1. Now we have the Grignard reaction. That X is too ugly to be left there. Okay. So in the Grignard reaction, we're going to start with some kind of carbonyl, right? And we are going to use the Grignard as our reagent. It's in the name, right? And so let's just do a simple old ketone. And let's use the same Grignard reagent we made here because this guy's sad and lonely. And we're going to make him blue because he's extra sad. Okay. Now, he is so sad and so alone, and he has this extra pair of electrons he just needs to share with someone. He just has all this extra love, and he wants to share with someone. So it doesn't matter whether it's an electrophile or if it's a hydrogen, he really, really, really wants someone. And so this means it's either a really strong nucleophile or it can be a really strong base. So I'm going to write that as a note here. So the Grignard reagent is so desperate for love, he can either attack a nucleophile or attack a base. I mean, it can either act as a nucleophile and attack an electrophile, or it can act as a base and attack a hydrogen. Sorry, I got very tongue-tied. I was talking so fast. Okay. So let's go back to the Grignard reaction, and I'm going to zoom in a little bit, but I'll zoom back out at the end. So, we know that we have this little delta plus here, and we have our little delta minus here. So this carbonyl carbon will serve as the electrophile. And Mr. Sad and Lonely Grignard over here is going to... Bam! These electrons are going to go up. And bada bing, bada boom. He's now in a relationship with Madame Carbonyl. And I really want everyone to count their carbons because people mess this up all the time. So Mr. Grignard had 1, 2, 3 carbons, and actually I'm going to go the other way just so we know what adds where. And so we have 1, 2, 3. Okay. So once we're at this point, we have a negative charge we have to take care of, and the Grignard reagent can't take care of it itself. So it's going to have a wingman over here, H3O+. So now the wingman comes over, and he's going to go ahead and donate a hydrogen to help keep his friend's new girl happy. So oxygen goes ahead, takes an electron. It uses its... Oxygen goes ahead and uses its extra pair of electrons to steal the hydrogen. And we get this lovely, lovely tertiary alcohol. And this is the story of Grignard. Do we have any... Nice story. Thank you so much. I've been working on a screenplay. I'm just waiting for Hollywood to get back to me. I'll let you guys know how that goes. But in the meantime, 0 through 5, how do we feel about this?
So basically, in most of these cases, it acts like a nucleophile and attacks the carbonyl. And then there's the other case where if it has like if it's like a carboxylic acid or whatever, something that has a proton, then it acts like a base. What was that case again?
I'm going to go over that in just 1 second. I just wanted people to be able to
Okay.
screenshot, but that's a good point. We will talk about that. And someone asked, you don't ever want to end with a negative charge, right? Yes, so you don't really ever want to end with any kind of charge. You want to try your best to end up with something that is neutral. All right, so someone said something, made a really good point about, like, when does it act like a base, right? And so our whole love story can be ruined if we have an acidic hydrogen present. And let me talk about that. I'll write it down. So acidic hydrogen equals no reaction. So an acidic hydrogen is going to be a carboxylic acid, an alcohol, or a triple bond. And I'm going to just highlight the hydrogen I'm talking about. So all of these 3 hydrogens are considered to be acidic hydrogens in this case. And if these are present anywhere in this reaction, our homeboy Mr. Grignard over here is not going to want to go for... Sorry, I got too excited. Is not going to want to go for this carbonyl. Instead, it's going to snatch this easy hydrogen, because it's already super acidic, and it ends up just doing an acid-base reaction. So, for the purposes of the Grignard reaction, we say that there was none. And I will repeat myself, and then I'll allow you guys to screenshot. So, if we have an acidic hydrogen present anywhere in this mechanism, so any part of this, right? This Grignard right here is so powerful that instead of wasting its time trying to get with the carbonyl, it's just going to snatch this acidic hydrogen because it's easier to grab. When it snatches that hydrogen, we end up having an acid-base reaction. So we would call that no reaction for the Grignard. And I will draw a little example just so it's not like super ambiguous. So let's say I had something like this, right? And I'm reacting it with Senor Grignard and H3O+, right? Instead of attacking the carbonyl, it's going to act like a base. It's going to steal the hydrogen. And we're going to get plus this. Right? This was not a Grignard reaction. This was an acid-base reaction. So we would say that this had no reaction. Because acid-base is not Grignard, it's no reaction. People kind of get confused about that with like, oh, but it was a reaction, it just wasn't the Grignard. So yes, we want the Grignard. So if an acid-base reaction happens, it doesn't count. Also, my dog saw a cat and he's freaking out. Please ignore that in the background. And now I will zoom out so you can take a picture. Ta-da. So how do we feel now? Is anyone super confused by the hydrogen rule? Makes sense. Okay, cool. So I'll give it another second to screenshot and whatnot. Someone said, I feel it's the first time we're going over this, so I suggest looking at it a couple times, doing some reactions, doing some practice problems, and you should be good. Okay, so let's go back up here to the handout, and we're just going to go ahead and fill the answers in. So a Grignard can be both because it has carbon with a negative charge. So the nucleophilic species is going to be this. Because remember, we cut this part out of our lives. And the Grignard reagent will act as a base when there's an acidic H present. Ta-da! Alright, so I'll give you a moment to screenshot this. We already did the first example, so we'll do some more when we get to the practice problems hour. Does anyone have any questions about Grignards so far? I'll give it a moment. Does anyone need me to go anywhere else to take a screenshot? Because I'm going to leave the Grignard handout. Okay, cool. So it is 6:24. We are going to take a quick 5-minute break until 6:30 so I can go back into the other handout, and we're going to do chapters 13 and 14 super quick. So we're now done with 11 and 12, and we're going to take a 5-minute break until we do chapter 13 and 14. So I'm going to pause the recording. All right, so let's go on to chapter 13. Chapter 13 is pretty straightforward. It's pretty short. So conjugation, first and foremost, I just defined what a diene is in case you still weren't sure. A diene is when we have two double bonds on a carbon chain. Di, two, ene, double bond. Now, when we have two double bonds separated by a single bond in the middle, we call that conjugated. When we have two double bonds separated by more than one single bond, we call that isolated. And then when we have two double bonds attached to the same carbon, we're going to call that cumulated. And then when we talk about stability, conjugated is super, super, super stable. It's good. It's awesome. We love conjugated. Isolated is meh. Cumulated is super unstable. So the order of stability goes like so. Most stable. Least stable. That's pretty much all there is to conjugation. I'll give it a moment in case you have to write anything down. So configuration versus conformation is something that we spend a lot of time on in SI, but I want to give you like this, the most important takeaway from it. So configuration is, I truly don't know why these lines got deleted, but this is supposed to look like this. So configuration is when you have a single bond sandwich with a double bond in the middle. When we are looking at the double bond in the middle, and we cut it in half, if our two priority groups are pointing opposite directions, we can call that either E or trans. If they are pointing in the same direction, you can call it Z, aka cis. And we're going to say that E is more stable. And we are also going to say you cannot flip between E and Z. You cannot rotate freely along a double bond, so you cannot flip between these two configurations. For conformation, however, again, I don't know why this double bond was deleted. I hope it was showing up for everyone else. So we're going to call it S-cis and S-trans because now we have a double bond sandwich with a single bond in the middle. And when we're trying to figure out what the conformation of the single bond is, we're looking at both of these double bonds. So if the two double bonds are pointing opposite directions, we call this S-trans. And if they're pointing the same direction, we call that S-cis. We know that S-trans is more stable. And we actually can flip, and I'll say rotate actually, between conformations. So we have free rotation along this single bond. So we can rotate between S-cis and S-trans. That is pretty much it for configuration and conformation. We did this example in SI and we took like 10 minutes to do it, so I don't want to spend too much time in the exam review because we are a tad bit behind. You can watch this explanation in the SI session. Recording, obviously. So I'll give you a moment for any questions, comments, concerns, and for screenshots. And then we will move right along. Alright, there's no one Has any questions? Let's just go to UV spec. Alright. So, I put this here as kind of like, it's not exactly part of UV spec, it's part of molecular orbital theory. I just put it up here as like an extra thing that we didn't cover in SI. So, I'll just draw a line right here so you know that they're two different things. Alright, so as far as UV spectroscopy goes, again, it's pretty straightforward. All you really need to know is that UV spec tells us the level of conjugation. So we know that the higher the number of double bonds in conjugation, we have a lower energy, which corresponds to a higher wavelength, aka longer wavelength, and a smaller frequency. So again, UV spec tells us the level of conjugation. The higher the level of conjugation, aka the more double bonds we have, the lower the energy, the higher the wavelength, and the lower the frequency. That's pretty much all you need for UV spec. Alright, so now molecular orbital theory is going to take a few minutes. We're going to do this one last, so we're going to come back to it. Don't forget about it, though. Okay, so there is a lot to draw here, so I pre-drew a lot of it for myself and for you guys. I didn't want to waste too much time. One thing that I included here that I didn't include in the SI session is these little nodes. There wasn't any particular reason, I just forgot to talk about it during the SI session, and I thought I'd just mention it here in case anyone was super confused about it. But it's not really a big deal, it doesn't really mean too much. So, basically, the lowest energy level is when all of the orbitals are pointing in the same direction. And then when they are flipping, they create these nodes in between them. And that's what makes it a higher energy. So all you need to know conceptually is that the lowest energy level, they're all colored in on the same side. AKA they all have the same spin state, or they have the same spin, excuse me. And every time you go up in energy level, you add one node. So you add one node. On pi 3, you have two nodes, and on pi 4, you have a node between each orbital. A couple semesters ago, I got super excited about this because I learned about what exactly this means in advanced orgo, but also I realized that nobody cares because it's not important in this class, and it tends to be really confusing, so I'm not even going to bother going through what all the nodes mean and all that. It's drawn here for you in case you're interested, but don't pay too much attention to it for the exam. Okay. Now, let's talk about 1,3-butadiene. So 1,3-butadiene has two double bonds. Each of the carbons on these double bonds have one electron in the p orbital. And so each of these electrons counts as a pi electron. And each of these p orbitals counts as an atomic orbital and a molecular orbital. So we have 4 AOs, 4 MOs, and 4 pi electrons. And I'm going to do my pi electrons in purple. We fill up the first energy level, and then we fill up the next energy level. So in the ground state, we have 4 bonding electrons and 4 bonding electrons. In the ground state, we have 4 bonding electrons and 2 bonding orbitals. We have 0 anti-bonding electrons and 2 anti-bonding orbitals. But wait, Rosemary, how do we know if it's bonding or anti-bonding orbitals? The way you know that is we have 4 total molecular orbitals. So we're going to cut this in half. And anything under the line is bonding, anything above the line is anti-bonding. We know that because there has to be an equal number of bonding and anti-bonding. So there has to be 2 and 2. All right, so in the excited states, this is true for all of these. All we're going to do is we're going to take one of these electrons and move it up. So it goes from this to this. And someone asked in the chat, you always fill in one energy level before continuing to the next? Yes, exactly. So we're going to fill in 2 and then go up 2. And there's something special about the movement of this electron to pi 3. And we're essentially going to say that the highest occupied molecular orbital, or the HOMO, is going to donate an electron to the lowest unoccupied molecular orbital, or the LUMO. So the HOMO is the highest energy level with an electron in it, and the LUMO is the lowest energy level without any electrons. When we go from the ground to the excited state, the HOMO and the LUMO do not change names. So pi 2 is still a HOMO, pi 3 is still a LUMO, but temporarily there will be an electron in the LUMO. And then it jumps back down to this. Any questions on the basics of the molecular orbital theory diagram for 1,3-butadiene? Because all the rest of them are pretty much following the same principles, just different electrons. You guys are feeling 5? Hell yeah, dude. Okay, so the other thing I'll fill in... Yes, what's up?
Oh, sorry, Rosemary. Can I just get the top part of what you wrote for the conjugation real quick? I just wanted to screenshot that because I don't think all this is going to fit on one page.
Yeah, no, probably not. I will do that. The only thing I wanted to add before I scroll up is there is going to be a star next to antibonding. All the star represents is an antibonding orbital. That's the only thing I forgot to mention. So here you go. And here, let me zoom in a bit. No problem at all. Okay. So, now that we got butadiene over with, let's do the allylic cation. Okay, so the allylic cation, anion, and radical are slightly different in that they have 3 molecular orbitals each. And now we don't have an even number anymore. So when we split it in half, we have 1 left over in the middle. So we have 1 bonding and 1 antibonding and 1 left over in the middle. The leftover one in the middle is going to be considered non-bonding. Excuse me, I'm so sorry. So again, if we have an odd number of molecular orbitals, we still have to have the same number of bonding and antibonding. So the odd one out in the middle is going to be considered non-bonding. So for the allylic cation, Cation means you have 0 electrons in the p orbital, but it's still sp2. So we still have an orbital here, but it's empty. So total, we have 2 pi electrons. So when I go to fill that in, we only fill up the first energy level. When we jump to the excited state, we're always going to move 1 electron from the HOMO to the LUMO. And we know that since this is the highest occupied orbital, it's the HOMO. This is the lowest unoccupied, so that's the LUMO. So we move 1 electron from pi 1 to pi 2. Ta-da. Again, the names HOMO, LUMO, bonding, antibonding are not going to change. The only thing that changes is where the electron is for a short period of time. Any questions? If not, here. It's probably easier if you do them 2 at a time, so I will let y'all screenshot this bad boy. And while you're doing that, I'll quickly, just because I can't help myself, explain what this means and why we have a non-bonding in the middle. So when we have an odd number of molecular orbitals and we make a node in the second energy level, we actually make our node right in the orbital. So this orbital is actually never going to have an electron in it. And so it's essentially like it cancels out. And so that's why we call it non-bonding. Don't worry too much about that. You won't be tested on that. It's just a fun fact. Question? Yes?
You said odd number, and what was it, the last part? Odd number of molecular orbitals
Yes,
and
so
something else?
there's an odd number, so the node goes right through the middle orbital.
Oh, gotcha. Okay. Okay.
Cool. All right, so let's do the allylic radical now. Pretty much the same setup as the one we just did, except we have 1 extra electron. Remember, anions, cations, radicals are sp2. So all we did is add 1 electron here. And so now we're going to have 1 electron, 2 electrons, 3. So pi 2 is only half full, but it's still considered the HOMO. The HOMO is the highest numbered energy level that has at least 1 electron in it. And since pi 3 is empty, pi 3 is the LUMO. So, excuse me, I don't know why I have the hiccups today. When we go from the ground to the excited state, the electron from the HOMO jumps up to the LUMO. So we keep our 2 here, and we jump 1 up to pi 3. Remember, this is a temporary state, so we don't change the naming of the HOMO and the LUMO. All that changes is that 1 electron. So the allylic anion, before I move on, yes, someone said, so it does not have to be full to be the HOMO. That's absolutely correct. So HOMO just means highest occupied. Occupied doesn't mean it has to be full. So it just has to have at least 1 to be considered the HOMO. To be considered the LUMO, it has to be completely empty, so 0 electrons. Cool, you're very welcome. Okay, so the allylic anion, we add 1 more electron, and so now we have 4 pi electrons. So we get 1, 2, 3, 4. So pi 2 is still the HOMO, pi 3 is still the LUMO. And when we excite it, we get this bad boy. So here, I will zoom out a tad so you can see both of these two. And so the big thing I want you guys to know, if he asks you how many electrons there are in the ground state, or in the ground state in the LUMO, the answer is always 0. It does not matter what molecule he asks about. So whatever he asks you about, if he says, how many electrons are in the LUMO in the ground state? 0. It's always 0. In the excited state, it's always 1. So I'll repeat that because this tends to be a time saver on the test. Wink, wink, nudge, nudge. In the ground state, in the LUMO, there is always 0 electrons. In the excited state, in the LUMO, there's always 1 electron. It does not matter what molecule you are looking at. All right. So now that we did that, we're going to go back up to this guy, right? And the reason I draw this out is because we talk about 1,3-butadiene, and Dr. West will sometimes try to be a sneaky sneaker and put pentadiene on the exam. And I'm just going to remove this plus sign for now. Actually, I'll keep it for one more second. And so people tend to get really upset and they're like, we don't know pentadiene, we only know butadiene. Well, I'm going to give you a sneaky little tip, right? Butadiene and pentadiene have the exact same molecular orbital theory diagrams. So I'm just going to erase all this for a second and start over. I'm so sorry to anyone who was working with the handout. I just couldn't stand the ugliness. Okay, so 1, 2. This pentadiene, it could be freaking octadiene, anything. There could be 100 carbons, but there's only 2 double bonds. And so there's only 4 molecular orbitals, so everything will be exactly the same as butadiene. And just to prove it to you, yes, what's up?
I thought sorry, but I thought with if that he explained that the like whatever the allylic position is after that double bond, that's also a pi orbital too. So wouldn't that one have 1, 2, 3, 4, 5 pi orbitals?
So if it had a cation, it would be, but that's why I got rid of the plus sign for now. I wanted to do it without the cation and then one with. But yes, you're absolutely right. If it did have the cation, it would be 5 orbitals.
I thought he just said, unless I misunderstood him, I could have sworn he said in lecture that I'm sorry, I'm brain fried at this point.
That's okay.
That the one at the very end, like in the allylic position of the double bonds, that those ones always have pi orbitals.
So I don't want to say anything against what Dr. West said. All I'm going to say is the way this is drawn, unless there's a cation, anion, or a radical, this would be sp3. So in the past when we've done this one, it was just considered sp3, so it didn't have anything special. So it was exactly the same as butadiene. But I will make myself a note just to email him and ask, just in case there's anything different for this semester. But, yes, I don't remember him saying that, so thanks, but... because what someone else said is that they think it's a pi orbital but no pi electrons, so that would pretty much be a cation. So yeah, I'm not exactly sure what he was talking about. I can also go back and watch the recording, so I will definitely do that and I will let you guys know. So I guess let's just skip this one right now because I don't want to say anything that contradicts Dr. West. And I will send an email update after I rewatch the lecture and I email Dr. West. Does that sound okay with everyone? Yeah? Okay, cool. So I will zoom out in case you want to take a picture of all of this at once. I know it's going to be pretty small, but I will give you a moment just in case. Okay, sorry for disappearing for a second. My mom called me and I was like, just wanted to make sure it wasn't any kind of emergency. Alrighty, so if y'all are good, I'm ready to move right along. Gonna skedaddle. Alright, so 1, 2, 1, 4. It looks like a lot, but it's really straightforward. So 1, 2, 1, 4 additions. I'm gonna zoom in. We have our double bond. The double bond acts like a nucleophile. It attacks the hydrogen and steals it. And we're going to break this bond and give the bromine the extra electrons. The hydrogen will be added to the least substituted side. Ta-da! And we get a cation right here. And,
I'm sorry, I have one other question. I'm sorry, I know I have a million questions today. With this one again, is it the reason that that particular double bond is the one that reacts? It's because of the benzylic carbocation is more stable than if the other double bond were to react?
So, okay, your idea is good, but it's not a benzylic. It would be the allylic. Because this isn't a benzene ring, it's just a cyclohexene ring.
Oh, I see what you're saying.
Yeah, so I like your idea, but in this one, since it is a conjugated diene, no matter which one you used, you would still get an allylic cation. The biggest reason that we use this one over this one is because, one, this one is substituted on one side and the other side, whereas this guy is substituted only on one side, which makes it more reactive. That's something he mentioned in lecture, but like super briefly. So double bonds are more stable when they have one substituent on each side than if they have two on one side. If that's too confusing for you...
Yeah, I remember that now.
Okay, good.
No, I forgot him saying that. Now I remember him saying that. Thank you.
Okay, good. No worries. The other way I like to think about it is this one is stuck in a ring, whereas this one is out in the open. So if it's out in the open, it's more likely to do the attacking. So once it attacks, we get this carbocation, and as Chase mentioned, it is allylic because it's one carbon down from the double bond. And so now we have our Br minus, and it can come in and attack the cation, and we would end up with, bam, bam, this product. But wait, there's more. At this point, instead of attacking, we could have done this fancy thing called resonance, and we could end up with our plus sign here and our double bond here. But Rosemary, what's the point? We get a less stable carbocation. Why would we do that? Well, my darlings, here we have a di-substituted double bond. Here we have a tri-substituted double bond. So getting a more stable double bond takes more energy because you're doing resonance, but overall, it's more stable. So we like this. That's why we would do that. And so now, the bromine is going to attack all the way over here. Boop. And our product looks like so. Bam. And the reason these are called 1, 2, 1, 4 additions is because I'm going to zoom in. And remember, the numbering here is arbitrary. It's not IUPAC. So we're always going to start with the carbon that hydrogen was attached to. So wherever hydrogen is attached, that's number 1. And so in this product, their relationship is 1, 2. So we call this the 1, 2 product. In this second one, again, we start here 1, 2, 3, 4. So their relationship now is 1, 4. So these guys are called the 1, 2 and the 1, 4 products. I'll zoom out so you can see the whole reaction. Any questions on just the reaction? All right. So I'm going to scroll down for 1 minute, and I'm going to show you this. And I didn't want to spend so much time writing down all this stuff, so I just wrote down the key points for thermodynamic and kinetic product, and I felt like me saying it verbally would suffice. So, when we're talking about kinetic and thermodynamic, I'm going to clap in between all my words here so you remember it. We're always talking about lowest. We're never talking about highest. So what I mean by that, kinetic product has the lowest activation energy. The thermodynamic product has the lowest potential energy. So if something has the lowest activation energy, we're not going to say, oh, that automatically has the highest something else. So this has to be this. No, we're only talking about lowest. And kinetic is lowest activation energy. Thermodynamic is lowest potential energy. So what this means is the kinetic product is formed the fastest, aka in the smallest number of steps, whereas the thermodynamic product is actually going to make the most stable product. And in the case of the reaction we just did, we can say that the kinetic product is the one that does not undergo resonance because it happens more quickly. And the thermodynamic product is the one that forms the most stable double bond. And I will go up here and show you again. So when we do resonance, we add an extra step here, and this extra step, like I said, takes a lot of energy. So this pathway is going to have the smallest activation energy. Whereas this pathway forms the most stable product because it has the most stable double bond. So all that being said, I'm going to have some participation. And we're going to go through these questions really quick. Please type in your answers. So A, B, C, D. Which one of these is the nucleophile? A. Perfect. Which one of these is the electrophile? B. Yes. Because that's the one being attacked. Which of the following is the 1, 2 product? I wrote that down already, so I kind of gave you the answer. C, yes. Which one is the 1, 4 product? Again, I kind of gave you the answer. D, yeah. Which one of these is a thermodynamic product? D, yes, because it has the most stable double bond. And which of these is the kinetic product? C, absolutely, because it did not go through resonance, so it happens in the least number of steps. Awesome. So when we do a reaction like this, are we always going to have one product that's kinetic and a separate product that's thermodynamic? No. Awesome. So sometimes the kinetic and the thermodynamic can be the same. So you have to watch out for it. As far as 1214 goes on his exam, this is a really good example to know. So if you know this one, you'll be prepared for whatever he's going to ask on the test. Wink, wink, nudge, nudge. Okay. So the last thing I want to do for this chapter is talk about these energy diagrams super quick. And usually I ask a lot of questions, but I want to go through it quickly, so I'm just going to go ahead and give you guys things. So we're going to say that this is our starting material. And A and B are our products. And so this bump is the activation energy. These lines are the potential energy of the products. Right? And so lowest, 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 we look for the lowest activation energy first. This one has the lowest bump, the lowest hill. So B is actually the kinetic product. And now we look for the lowest, lowest, lowest potential energy. For that, we're going to find the lowest product. B is higher up than A, so A is the lowest potential energy. So A is the kinetic, oh, just kidding. A is the thermodynamic product because it had the lowest potential energy, aka the most stable product. Now, if we go down to this example, and I will zoom out so you can see them both. Again, this is going to be our starting material. Activation energy. Activation energy. And we know that this is our potential energy. Potential energy. In this example, A has the lowest activation energy, tiniest bump, so A is actually going to be the kinetic product. And A still has the lowest activation energy and the lowest potential energy, so it's also going to be the thermo product. So in this example, A is both the kinetic and the thermodynamic product. So as promised, let me zoom out so you can see the whole thing. And if you want me to zoom into the first half and then zoom into the second half, I can do that as well. Now, so I will give it a moment. And then I'm actually going to stop the recording and start recording part 3. Because again, I don't want it to cut off and be weird again. All right, so we're pretty much done with chapter 13. How are we feeling on a scale of 1 to 5 about everything in chapter 13? And we haven't done Deals Alder yet. We will do that in a second, but... Feeling 5! Oh, yay! No, you're awesome. 4.5, that's awesome. Whatever you're at, I'm proud of you. You're here. You're doing awesome. Ooh, someone did like a little confetti explosion. Love to see it. Fun fact, I have a giant box of glitter and confetti under my bed. You didn't need to know that, but now you do. Okay, so I'm going to pause the recording.